Morning. I'm going to be giving the first one on supernova, why we study them. So this is sort of like the frosting, and then Danny Goldstein will be giving the cake after this, which is the real guts of how we do this. So I'm going to sort of lay the groundwork for why this is an important field. This is one of my favorite supernova, 2011 FE, and I'm going to get to why this was important and why sometimes real-time turnaround doesn't work, and then you have to go to plan B. What is a supernova? It's the explosive death of a star. They're the largest explosions in the universe. When they explode, the material is flying out of there at appreciable fractions of the speed of light, up to a fifth the speed of light. They outshine galaxies for a few weeks, made of hundreds of billions of stars, and in 1 month they'll emit more energy than our sun does in its 10 billion year lifetime. Nova means new. They were first used to describe new stars that suddenly appeared in the night. The Chinese have a much better moniker. They call them guest stars because they appear and they go away, and like a good guest, they leave. So I prefer guest stars. Super was added on by Fritz Zwicky in 1926 when they recognized that there was a difference between explosions which occurred in our galaxy, which had the same apparent brightness as some explosions which occurred in distant galaxies. And he realized that these were dramatically brighter, and so he called them supernova. And we've been observing supernova for 2,000 years, and I'll show you some of those examples momentarily. How frequent are they? Somewhere in the universe there's a supernova exploding every second. In a galaxy like our Milky Way, there's one supernova per century, roughly. And typical surveys that are going on right now generate about 1 to 3 supernova per night. And most of these are very distant. They're about 1 billion light years away. So here's an example. This is a supernova remnant. So the supernova went off in the year 1006. We can infer that by looking at the velocity of the material here and then projecting it back, given the distance, and then say, oh, it's about 1,000 years old. This was seen by observers with their eyes in Switzerland, Egypt, Iraq, China, Japan, and North America. It cast shadows at night and was visible during the day for several months. I am waiting for one of these to go off during my lifetime. It'd be very cool to point out to anybody walking down the street and say, hey, this is what I study. This is the Crab Nebula, images taken with the Hubble Space Telescope. And this supernova went off in 1054. It was bright enough to see during the daylight for 23 days and was visible in the night sky for almost 2 years. And this is a petroglyph by the Anasazi Native Americans, and this is an actual map of where the supernova was in the sky on July 4th, 1054. That hand is to give you an idea how far away it was from the crescent moon at that time, and that's an actual distance away that we can project back to that date when we knew it was from other archives in Japan and China when they recorded the brightness. So these are impressive events when they go off in our galaxy. And these are the two coolest supernovae because I think of it as the professor and the student. This is Tycho Brahe. He discovered a supernova by eye in 1572. This is its remnant today. And then his graduate student, Johannes Kepler, found his own supernova in 1604. My graduate students aren't going to be that lucky, I don't think, so, you know, tough for them. This is then the most impressive one, I think, that's gone off during my lifetime, supernova 87A. It was visible by eye, but unfortunately you had to be in the southern hemisphere. It went off in the Large Magellanic Cloud, only 170,000 light years away. And here is an image of the supernova expanding into a shell of material that the star, before it died, threw off, and then the supernova ejecta is running into it, slamming into it, and brightening it up. And this material came out maybe 20,000 years before the supernova exploded. We're still following the supernova today. It's easily visible 30 years later with the Hubble Space Telescope. So there are a couple different types of supernova. Core collapse supernova, these are massive stars, somewhere 8 to 10 times and more massive than our sun. They burn hydrogen to helium all the way down to iron. The iron core can only get so big before the protons and electrons get smushed together via nuclear physics and create neutrons, collapses rapidly down into a neutron star, and then there's some magic, and we still have no idea today exactly what goes on. We believe there's a combination of magnetohydrodynamics, the creation of all these neutrinos when you push the protons and electrons together to make the neutrons, and that throws off the outer layers of the star and ends it in its explosive death. There's another type of supernova, a thermonuclear supernova. These we call type 1a supernova. Binary system with some other star here and a white dwarf, a carbon-oxygen white dwarf that accretes material over. There's a limit called the Chandrasekhar limit, which is basically about 1.4 times the mass of our sun. As it builds up to that limit, and basically that's the limit at which it can no longer support itself via electron degeneracy pressure, a quirk of nuclear physics happens, the temperatures and densities go up incredibly, and you ignite carbon in a runaway thermonuclear explosion. And so these blow up. The problem is we don't quite know, we have some very good observations that these must be carbon-oxygen white dwarfs, that there's no other way to make them, but we have very little constraint on what's going on here. Is this a star like our sun? Is it another carbon-oxygen white dwarf and they spiral in together and that gets it above the Chandrasekhar mass and they explode? We do know that they're old in the sense that they're seen in galaxies which only have stars like our sun, so they can be up to 10 billion years old. So we know they're carbon-oxygen white dwarfs. We know they have some other companion, but the big search now is what exactly is the mechanism. So why do we bother studying these things? So we are star stuff, okay? As Carl Sagan said many, many moons ago when I was a kid, hydrogen and helium, traces of lithium, maybe beryllium from the Big Bang, and then pretty much everything else gets out through the explosion of a massive star. And more recently, we know from the recently detected binary neutron star merger that the heavier elements, the lanthanides, etc., are created from the merger of two neutron stars. So gold, etc., platinum down on the list all the way up to uranium. Interestingly, to make a binary neutron star, you need two supernova explosions to go off. So you have two massive stars orbiting each other. They both go supernova, and then eventually those two neutron stars coalesce and explode. So that's the first part, nuclear physics. This is the binary neutron star, what was going on. We have some very good theoretical models that made predictions, and the first one was seen and unfortunately was not discovered in a real-time survey. I think most of the ones in the future will be. I'll describe how that'll be done. This was discovered more or less by eye. We had some great theoretical models. They made predictions as to what we would see, and the predictions actually wound up matching the observations. We hope to catch a lot more of these so we can understand if the one we found just a few months ago is typical, or if there's a wide variety of these events and what they produce. Cosmology, this is another reason we love studying supernova. The type 1a supernova that explode at the Chandrasekhar mass, those supernova are unique because they have that trigger. They need to get up to that mass in order to explode. And because of that, they wind up being very, very similar in brightness. And so we basically wind up with what is a standard, 18 billion gigawatt light bulb out there that we can use to measure distances through the inverse square law. And this was work that was done here and at Berkeley Lab back in the late 90s. And, we've now basically seen that the universe is accelerating, and there's this force due to dark energy, and that was first discovered by using supernova as cosmic probes. So back in 1998, when I first came out to the lab, we were doing a search for supernova on the 4-meter telescope, the Victor Blanco telescope, down in the southern hemisphere. This is in Chile. You can see the Southern Cross, that's Mars. The image quality was a little bit better. We could see clouds here. This is Chris Smith, who was on the opposing team. We weren't goofing off. That night was horrible. I think we later played basketball in the 4-meter dome. They had a basketball hoop underneath it. I was a much, much better player than Chris was. He was on the competing team, so there was a little bit of a rivalry there. So I went up 10 points on him, and then I realized that being at 8,000 feet, sort of takes a tax on your body, and the score radically started shifting towards Chris, while I was just basically like, oh God, I gotta take a breath. But we would go back to back over 2-3 nights, and then they would have 2-3 nights, and we would find supernova. We were looking sometimes in different parts of the sky, sometimes not. So a very hands-on operation. This is sort of what it looked like. Down at Cerro Tololo, we'd image with 1K by 1K or 2K by 2K CCDs. We'd take 50 to 100 images across the sky. We'd come back just about a month later, not quite, and we'd take another set of 50 to 100 images. These would be sent up to Berkeley over what amounted to a modem, a 56 kbaud modem connection. That was good enough to get the data there in 24 hours. We would do image subtraction on it, and then students would hand scan this data and look for new events, a galaxy with a supernova on top of it. And then one night later, we would schedule follow-up at the Keck telescope in Hawaii and get a spectrum to tell us, is it a type 1a? Is it the ones we want to be standard candles to measure cosmology with? And then follow-up would then be triggered for the ones we liked at the Isaac Newton telescope on the Canary Islands, the Wind telescope in Arizona, or the Hubble Space Telescope in space. And we'd monitor these for a couple months, measure the peak brightness, and then do our cosmology work with it. And this was basically the team there. And most of the younger people here were the ones who were looking at this imaging data. Basically, not quite blinking it, but say coordinated blinking. We'd use the computers to tell us where a good bright spot was, and then we'd look at it. And this is sort of what the differencing image looks like, with lots of garbage. And it was just running on a cluster of computers, nothing too terribly fancy. There was a search for nearby supernova. This was done basically on photographic plates. And then ours was the first digital supernova. And we made this diagram of brightness versus the expansion that we measured from the galaxies and how fast they were moving away from us. And we measured that the universe was actually accelerating. Okay, and so very quickly, you'll notice here that the number of supernovae they find at low redshift was comparable to the ones that we found in high redshift, very distant ones. And this is just a geometric effect, okay? I do something like this with my detector. I have one person here in the front row and 6 or 7 of you in the back row. It's easier to find things farther away with the given detector. And so we rapidly realized that, even if we just continued on, nothing new changes to our detectors, whatever. At high redshift, we would start to dwarf the number of supernovae that we had nearby that we need to anchor what we call this Hubble diagram here. And so this became our challenge, is how do we increase the number of supernovae there at low redshift. So this is everybody at the 2011 Nobel Prize ceremony won by Saul Perlmutter, Brian Schmidt, and Adam Rees. We all wore our penguin suits, and at that time we were in the middle of really pushing both high redshift, doing new searches with the Hubble Space Telescope, but going after much, much better ways to get low redshift supernovae, because this was our biggest challenge in terms of making a finer measurement. So this is sort of what real supernova detection looks like, and this is what Danny's going to talk about, is what is the math and what are the algorithms behind it. But per image, 2K by 2K image, we'd have about 205 sigma detections. So this is something you can't see by eye, just in a single. This is the new image, this is the reference image, you subtract the new from the ref, you see the supernova. You can't see that without doing the image subtraction, but in the image subtraction it sticks out pretty well. Here though is a piece of garbage. This is a star that saturated in one image, didn't saturate in the other, left some residual, looks like garbage. Here's another one because the star actually moved. Stars move, it sucks. So we put a lot of cuts in, and then, like I said, we triggered basically a human to look at the position where those cuts were made. Danny's going to talk about how we took that to the next level and automated it. But we were only taking, say, 100 images a night. We had 205 sigma candidates. It's 20,000 objects. Okay, we'd cut through them with some cuts, maybe get it down to 10,000. We had 10 students, so each of them look at 1,000 objects. It takes you about 5 seconds to look at an object. You can rip through this in a few hours. And that's the way we were back then, and that's what we did. We just brought in students. The problem was when we started to work on the nearby searches. And so these are the first 3 searches that were done. One was done at Haleakala on the 1.2 meter telescope, and then there were 2 successive surveys with different instruments on the Palomar telescopes. But just start looking at the data here. Instead of doing 5-10 minute exposures on a 2K by 2K CCD, we had 4K by 4K CCDs, and we were doing 20-second exposures. Okay, and the rates of data started increasing dramatically to 12 gigabytes a night to 28 gigabytes a night when we got over here on the second iteration of the Palomar telescope. And this was just a few years later, 3 to 5 years later, in 2001. And okay, you still get the same number of false positives. Okay, it's a pixel star thing. It's not because we're staring deeper, we saw more of these things. We get the same 200 per image that we took. And so multiply this up, okay? Doing 1,000 square degrees a night, this was a 250 times increase in scale per night. And by the way, we'd run this survey every single night. It wasn't like we'd go out and observe in October, come back in November, and then do our follow-up from December to January. This was find a supernova tonight, start following it with this telescope. Find a supernova tomorrow night, follow it up, boom, boom, boom. So this was constant. This is where we really had to start getting clever. And for a while, we did it with humans. And then, as Danny will show in the next talk, how we got around this. The other interesting thing was bandwidth, data transfer. I had a professor in graduate school who said never underestimate the bandwidth of a station wagon filled with DAT tapes. And there is something to that. Actually, when we were doing this survey in 2000 down at the telescope in Arizona, we would take a rate array of disks. We had 3 of them. They each had about 5 terabyte capacity at that time, very expensive. And we'd have one down at the telescope, one at the lab, and one in transit via FedEx, and then later we switched to another thing. Should have seen them after 2 years. They were dented on the sides and everything. But it could get back to the lab in less than 24 hours. And we just plug it into our cluster and start doing the search, okay? Things had to change as we moved forward, and then this was the big change. The one in 2011 was telling you we were neck deep in at the Nobel ceremony there. We were still worrying about this. And so Palomar Transient Factory is the one I'm going to talk about. It just finished up in 2017 in the spring. We're getting ready for a new survey now, which, by the way, just I heard last night, made its first extragalactic supernova discovery, which was just confirmed. It's the Zwicky Transient Facility. I'll show you where we're going with that in the near future. But to show how different this is, you know, we had a 7.8 square degree field of view. I'll show you what that looks like. We were taking 1-minute exposures, and then we started cranking on this in 2009, and we had two cadences. We did one where we were searching every night, sort of for the faster transients, maybe in nearby galaxy clusters, only 60, 100 million light years away. And then a survey that sort of went on 3 to 5 day time scales, covering a good, large chunks of the sky. Down at Palomar, in the mountains between LA and San Diego, the 48-inch was our discovery engine. And then, as Dick mentioned, we want to feed other telescopes with real-time discovery, and the 60-inch was one of the main drivers there in terms of finding things here, and then as quickly as we could, pushing them over there. FedEx no longer going to work, so there is this network down there called HP-REN, set up to basically provide networking services to the Native Americans who had their schools and such here. I'll describe actually what their bandwidth is mostly used for later. And microwave relay towers that go over the mountains and then down to San Diego. And so Palomar is here. We piggybacked off of this network, sent it down to San Diego Supercomputing Center, and then it came up on the network here to ESNet. So this is what the camera looks like. There was one dead chip. Here's the size of the full moon, so you can see how big a chunk of the sky we're doing. The camera has 1 arcsecond resolution. That's about the size of a dime at 1 mile. So it's a fairly impressive resolution. And like I said, taking 60-second exposures, it gets down to 21st magnitude. That's about 1 million times less bright than you can see with your eye. Okay, so that's sort of the depths of the faintest objects that you can see on here. By the way, when you're looking at these, the majority of the smudges that you see there are actually galaxies. They're not stars. And so this gives you an idea of how we can get up to a rate of 1 supernova, 3 supernova a night. If 1 supernova blows off per century in the Milky Way galaxy, if we look at 100 galaxies, we'll see 1 a year. If we look at 10,000-ish galaxies, we'll see 1 a night. Okay, so that's sort of the statistics that we're dealing with. So we had to look at sort of that number of galaxies per night. Now, there are a whole bunch of different science projects. It wasn't just supernova. That was a good chunk of it, but people were looking at other types of odd things that would blow up. Cataclysmic variables. People wanted to study variable stars, measure their light curve shapes. People wanted to follow up black holes that all of a sudden sucked in a nearby star or gas and exploded. People were looking at near-Earth objects, etc. The cool thing about this is we all work together, and our follow-up programs were all coordinated. Since if you see a smudge of light, you don't know exactly what it is, right? It could be something very distant, could be something nearby, just along the line of sight, you don't know. So all of the groups would pool together follow-up time from all of these different telescopes to trigger on these events in real time. And so as a community, we worked on these problems together. And this was the real power of the entire program, was the ability to trigger on this follow-up in real time. And the closer to real time, as I'll explain in the second half of my talk, the better, okay? If you looked at the cost of the survey, the maintenance of the telescope and running the operations was about 25% of the total budget. Another 25% went into the computing and the algorithms and the interface to set it up and to find these things rapidly and to turn around on it. And then half of it went into the follow-up telescopes. So if you're trying to use your money effectively, what you don't want to do is give these guys bad things to follow up, because that's where you're spending your most bucks. So that's what we looked upon in terms of operations and in terms of writing our algorithms, is how do we optimize the science that these guys are triggering on. So this is sort of the workflow that we have. We take the data at the 48-inch, comes down the microwave relay and then to ESNet, and then came to the National Energy Research Supercomputing Center just up on the hill there through a data transfer node. We would do image processing to trending. So you get a raw image, you'd have to take off the bias, there's a flat field. You do that, you'd solve for how deep the image was, were there clouds at night, etc. You solve for things like that. Then you run image subtraction. You even might stack the data. And then you do things like create a reference image if you haven't had one already. Solve for the astrometry in there to line up the two images so that you could run the image subtraction. And then we go through basically what Danny's going to talk about is how to identify in the sea of junk, basically 1 million objects a night. We would find of those basically 1,000 were interesting astrophysical transients, and of those, one of them was a new transient. Okay, so it's a 1 in a million type thing. That's what goes on here, but we also compare to known stars or asteroids, and then we have triggers. There were triggers that would wake somebody up. There were triggers that would automatically slew a telescope without human interaction, etc. And we got these triggers down to about 40 minutes in our first pass with the Palomar Transient Factory. Okay, and so here again, here's a typical image. You can see all the garbage back there. This is the only interesting object. And so like I said, it's sort of a 1 in a million type thing. This is what we wound up doing in the Palomar Transient Factory. We took 1.82 million objects in a red band and in a green bluer band. Took about a few 100,000. Made over 1.5 million subtractions. We had coverage almost on the entire northern sky that you could see from Palomar. We had about 1 billion candidates in our database, but of those that were interesting, just below 50,000. And this was done in 851 nights. So this is how we started off. We were running it on a IBM iDataplex machine called Carver. We had a very generous donation from NERSC to work on one of the first real-time pipelines that they had there. We had real-time queues that we could send into to run on, and we basically filled up this entire space, and we had a database that was about 1 terabyte by the time we were done, sitting on one of these Science Gateway nodes. Eventually, this pipeline was replicated by 3 other surveys. Danny will talk about one of the other ones, the Dark Energy Survey, that used this pipeline to great success up there. So this, back in 2012, Josh and I were observing at Keck one night, and well, we weren't in Hawaii, we were actually just sitting about 300 yards over there in the basement of Campbell Hall, and we said, you know what? We were doing things with about 24-hour turnaround, and we said, why don't we try to do something in the night so we can slew and look at something with the Keck telescope at night? And it's a great thing. We had about 3 hours time delay. So Sky swings around 24 hours. The difference between Palomar and Hawaii is about 3 hours. So that gave us a 3-hour window to find something at Palomar, and then it would be directly overhead by the time we were on at Keck. So what we did was start to push the pipeline in by hand. So I talked to the people at NERSC, got some queues up. Josh was there with his machine learning algorithms that Danny will talk about, and we just started sitting there and doing it in real time. And we triggered on a supernova that actually wound up being one of the youngest supernova that we ever caught to that point. And that's where we said we have to automate this. And so we automated it, and I would say about 3 months later, we had it running at where most of the candidates, from the time the shutter closed at Palomar to the time we had a candidate in the database and we could do something actionable with it, like trigger another telescope or wake somebody up to take a look at it, or more likely alert our European collaborators who were in the middle of their day, was about 1 hour for the worst case, and the median turnaround time was about 30 minutes. And so we had a bunch of discoveries that kept on pushing us to younger and younger times. So when the Palomar Transient Factory shut down in December of 2012, they started a program called the Intermediate Palomar Transient Factory, or the Interim Palomar Transient Factory. I don't know. It was the bridge between the Palomar Transient Factory and the Zwicky Transient Facility. And I took everything offline for 1 month. We rewrote the entire pipelines and we pushed it through. There was a nice project funded by DOE called Extreme Scale Scientific Workflow Analysis and Prediction. We used them to basically go through and do everything from understanding our file systems, database queries, etc., parallelizing our codes. And now you can see the time in seconds, and this is a logarithmic scale. We were doing basically everything in 5 minutes. We instrumented our pipeline for timings. This was the most important part. Every single step, there are about 39 steps. We had a ping to the database to say it took this long to do this. We got to where you're running several of these simultaneously. We knew more about the NERSC Center than they did in real time. We were querying some part of the NERSC Center, from data transfer to file system I/O to how quickly a job started up on the real-time queuing system every quarter of a second, okay, throughout the entire night. We fixed things like how long it took to load Python from their libraries. We looked at it and said, this is ridiculous. It's taking 60 seconds to load it up. And they realized that there was an error in the way that they put the libraries into their system. We moved all of the I/O to a Luster Scratch file system that made it much, much better. We optimized our databases up the wazoo. And then this guy, Yi Kao, he was the one who did it. I basically gave him a list. I said, here, take my old horrible pipeline that was written in Bash, Perl, Fortran, C++. I had some other languages in there. Oh, there was Java. There was some of Josh's Python. And I said, just redo everything in Python with calls to some C libraries. He did that. We tweaked up our database. He got it going great. He got this eScience fellowship at UW, and he was going to start working on LSST, and then Google sucked him up just like that. And he's like, well, they offered me 2x my salary in stock options. What should I do? And I'm like, what do you think you'll be happy doing? And he's like, well, I have a daughter now. And I'm like, well, okay, take the job if that's what you want. And he's been there now just over a year, and he tells me he's very happy. He's working in their research center and enjoying it quite well. Okay, so this is a list of all the things that we did with these 39 checkpoints. So this is what it looks like. This is just one of the checkpoints. How long does it take to transfer data from the telescope up to NERSC? And you'll notice that it takes longer at the start of the night. This is around 7 o'clock at night. And then that speeds up, and then in the morning it kicks up. So I had the folks at ESNet do an analysis of the network and say, hey, what's going on? What is the traffic on the HP-REN network that causes the slowdowns here and here, but things are relatively smooth? And they said, well, you know, at first guess, before even looking at it, my guess is this is most people coming home and you know, looking at news and things like that. And then here they're waking up in the morning and they're doing some stuff. And then during the middle of the night, turns out almost all of this traffic right here is from the Indian gambling casinos that are in the mountains outside of Palomar. And this, they identified the bulk of the slowdown was due to horse racing in China that they would live stream at the casinos so people could bet on it, okay? And I was just stunned. But, okay, so we did not file any official things because they're allowed to use it whatever way they want to use it. But this does allow you to think about how you optimize your survey. If you know it's going to take 160 seconds to transfer an image here, maybe you do fields which don't require as much real-time turnaround as, say, a field you could do here. So say the people that want to just characterize variable stars, they go up and down and up and down, they just want good coverage, they're not reacting to anything, okay? They just want the statistics. So you look at the galaxy at the beginning part of the night, and then you look at the extragalactic fields during the middle of the night, where you have supernova, where you want to turn around immediately. So optimizations were put in to do some things like this with the survey in the last year. We started to look at things like the number of candidates divided by the time that it took to process them versus the median time. And what we noticed is the more candidates that you had on an image, the longer it took to process. This is not surprising. Every candidate, you have to query the database, see what was there before. You have to run more machine learning algorithms on it, et cetera. So this trend wasn't so surprising, and a lot of this can be parallelized. But it was this trend. Why do we get these several sigma outliers that take so much longer? Almost all of this was due to glitches at NERSC. Things like there was some issue with the I/O system, or there was some networking issue, and would cause 3-4x delays in what we were expecting. So, you know, we put some uncertainties on this, and then when we got any of these that would come up during the survey, we'd send a message to NERSC, look at the checkpoint and say, oh, this is a networking type issue, this is a processing type issue, this is a file system issue, and just send them a little notice. And then if we look, you know, this is another way of looking at that, and you can see the outliers here. And now we're working on a project with them because they're moving to the idea of having a super facility, the idea of running workflows like this in real time. They want to know about these issues, so they're teaming up with us to work on a project where they can understand these outliers, see how they're responsible for it, and then work to tweak up the system to mitigate this, to provide a certain level of surface for real-time analysis. So this is what we wound up doing at the end of these two surveys. We identified over 3,000 and typed them spectroscopically supernova. We had 100,000 galactic transients and tens of thousands of transients in our nearest neighbor, M31. These are the images we took. We tended to stay away from the galaxy until the last few years. That's the galaxy here. And of course, we can't see down in the south. But these are the number of images going up from the orangish, which is about 10, to the white, which is about 1,000 that we took. Over 190 publications, 7 in Nature and 3 in Science since 2009. So it's quite a successful survey. So here are some of the science things that we were able to glean out of the program. So one of the things, if you find a supernova, you might ask yourself, what happened before the supernova went off. So we got a supernova, we saw these hydrogen lines in the supernova that suggested it was running into something that was out there. Question is, when did that something out there go off? We went back in the data, so this is sort of our limiting brightness, this is time, and you know, here was our first detection, and then the supernova screamed up, and we went back and we stacked images from earlier, and we found pre-outbursts that went on. And this was actually the star undergoing some machinations where it sloughed off some of its atmosphere and threw it out at several hundred kilometers per second right before the supernova explosion. We now think this happens in most of the massive stars, sort of in the 20 solar mass range, that this is happening more often than not. So now one of the things that we decided to do was, let's add in another type of image processing, which is we'll take all the images from the week, stack them together to go deeper, so that we could go down and detect these things, so that we could see a little burst. So while we had the supernova and we could take spectra here, it would be really cool if we could have found it back here when it had one of these pre-outbursts, so we could study the exact nature of that pre-outburst in a lot better detail. So now we're running two pipelines. We take data for a week, we stack it, we look for things, and then we run the nightly one on top of it, and we try to do things that way. And so this is sort of a schematic of what was going on with this supernova. Supernova blows up, there's a cloud, it lights it up, making all these hydrogen lines, and then it runs into it. We have these things called gamma ray bursts. Gamma ray bursts, some chunk of them come from supernova that produce jets and create strong beams of light. Unfortunately, gamma rays are hard to detect. They basically have these box-like detectors, 4 of them on a spacecraft. They get hit by gamma rays, they sort of triangulate back. Sometimes they can do this very well, like precision down to I can point any telescope in the world at it. And sometimes they just basically tell you, yeah, it's somewhere up there, okay? And so you have to go searching. This is one of the searches that we did for one of those ones where it wasn't what we call well localized. And so you can see the images that we took, and then we saw this transient go off in this field. And we want to get on these very quickly because these things drop like a rock in brightness. If we were 24 hours later, no chance of seeing this. And on top of that, you're going to find so many transients in these fields. The one characteristic about these is that they're dropping quickly during the night, whereas almost all the other transients, they'll be bright. They might change by 5 or 10%, but they're not going to drop by a factor of 2. So not only do you want to hit this once, you want to hit it several times and watch this thing go down. And so that's what we were able to do. Another one came along, and so now we are quite good at this, and our next survey is going to really be using this where things are poorly localized from other areas of astrophysical searching. We can do follow-up and pinpoint these afterglows. Orphan afterglows. These are basically gamma ray bursts for which there was no detection of gamma rays, okay? This can happen for a couple reasons. One, the gamma ray signal is not strong enough, and the other is that that spacecraft or spacecrafts aren't looking in that portion of the sky. They can't cover everything, okay? And so here you can see how rapidly these are falling in brightness. Each magnitude is a factor of 2.5 in brightness. So just over the course of a half a day, this is dropping by almost a factor of 10. And this is what it looks like. There's nothing, there's something, okay? And you go and you look in deep images, you can barely see anything, and then we take a spectrum of this, and this was incredibly high redshift. This is almost 8 billion light years away. It's a gamma ray burst pointed at us, okay? Flash spectroscopy. There are some interesting supernova, and this was one of them. We found a few of these now. So you have a whole bunch of non-detections, and then boom, you see the supernova, and during the same night, it screams up in brightness. And we were able to get a spectrum just a few hours later at Keck. And then we started triggering follow-up on all of these different instruments. So this is the number of hours. So we took an image here, we wait 45 minutes and we take another image. We use that to rule out asteroids, because asteroids will move. We take 2 images. If it's at the same location, we're pretty sure it's not an asteroid. Second image comes in, then we have an automated trigger. We took a spectrum just a few hours later at Keck, and then we started triggering the Swift Space Telescope, follow-up from the ground from the Las Cumbres Observatory, the VLA, the Very Large Array of Radio telescopes, and the Karma telescope, and all of these were triggered within 8 hours of detection. And this is what we saw. We saw a spectrum very early on that looked like a star spectrum. A star that has a very, very quick wind. These are called Wolf-Rayet stars. Here are a whole bunch of different models. Actually, these are actual observations of different Wolf-Rayet stars. And then this is the spectrum that we got, so we could actually see what type of star exactly this was. And we were like, a supernova explosion. Why would we see that? What it was the supernova was very far down. There was this wind that was out there, and the supernova just acted like a light bulb and just lit up the surrounding gas so that we could see it. We could see what was there. And then what happened was that the supernova ejecta starts expanding, and now it's becoming a substantial fraction of the brightness of the object there, and it starts to dominate the spectrum. You can see some of the lines now are just, fading away. You can barely detect it just a few hours later. And then finally the supernova sweeps over all that material, and all you can see is the supernova and its high velocity material, and that's it. So these are observations that only exist for the first 12 hours, and it points back directly to what type of star blew up. So quite important, quite quick turnaround observations to get. This is one of my favorite ones where the pipeline's entirely screwed up. So we were doing a survey in the bluer bands, a G-band run. It's only about 500 square degrees, hit twice during the night. And it was split half and half between the nightly cadence and these 3 to 5 day cadence. And we found 10 new transients that night. And unfortunately, the supercomputing center updated the kernel on all their machines during the night and didn't tell me. And so the pipeline completely failed because I had to recompile all the code. So I recompiled the code at about 6 a.m. and then started up the pipeline, and things started going through. And then there was another problem at Caltech. They had just changed an IP address, and we couldn't have this automatic saving, so we had to save things by hand. And so what do 2 young people do, like Josh and myself? We start looking at things that the machine tells us to look at, and then we start saving them by hand. And Josh found this beautiful one. You subtract off the 8 hours, you can see what time of day we were doing it. And he said, woohoo, look at that, awesome. And then I found this one right here, and I said, I see your 20 and raise you 100. And this was the supernova. If you zoom out, it's the one I showed on the very first slide, 2011 FE. It was caught about 100,000 times fainter than the eye can see. There was a 20% rise in the first 2 detections, separated by 1 hour, so we knew we caught it very young. And it was caught at 1/1000th the brightness that it would reach when it finally hit peak brightness. We sent out a telegram just a few hours after that. We were able to slew a telescope in the Canary Islands to get a spectrum just before, just literally after sunset on the Canaries. We got this one in, and we sent out an alert, and pretty much every major observatory started following up this supernova. So not quite real time, but close. So here's the nice image. This supernova is still being followed even to this day with the Hubble Space Telescope. We were able to divine from those very early observations and non-detections that we had the night before that the only thing small enough to produce that was a carbon-oxygen white dwarf, something we had assumed many years due to the nuclear physics, due to the materials that were burned. We were able to say the only star that could basically cause this supernova was a carbon-oxygen white dwarf. Here's another thing, gravitational wave. This is all the rage with LIGO, the gravitational wave detector. Here is one of the issues. It's very similar to the poorly localized gamma ray bursts issue, is that the gravitational wave detectors, even with 3 of them online right now, sort of give you a chunk of sky, maybe 100 square degrees, 200 square degrees, in which you have transients. This was the first one, black hole merger. We weren't expected to see anything. We still went after it. You can see here are all the supernova that we actually found. Had nothing to do with the gravitational wave trigger. So these are sort of 1 in a million type objects. You've got to wade through all of these before you actually see something that you would expect. So it requires paving over the sky, and I'll talk about how we'll do that. So sifting through all of these, getting rapid spectroscopic follow-up so we could characterize it, and just basically finding a bunch of supernova. So let me skip through. So this is where we're up to, Zwicky Transient Facility. So this is PTF. This is one you've probably heard about, LSST. This is the size of the Zwicky Transient Facility. It's a 47 square degree imager. It's absolutely huge. If you compare it to PTF, it is more than an order of magnitude faster. They'll be taking 30-second exposures instead of 60. They have 47 square degrees instead of 7. And so it will just basically, it runs out of sky before it runs out of time, okay? So they will basically be observing the entire extragalactic sky every 3 nights. And that's what's going on with this imager. They just started observations. So this is one of the issues that we'll have with ZTF to some level, but we're definitely going to have with LSST. So this is, for me, an absolutely boring transient. Goes up and down, some variable star. Okay? And these are non-detections, upper limits on how deep our survey can go. So we're not finding this object at all here. Okay? And these limits go up and down, and there are gaps between them because we have weather. So that'll block out some observations. We'll have clouds sometimes. More often than not, we'll have the moon. The moon makes the sky brighter. It's harder to see things, so we don't go as deep. And then all of a sudden, we get over to this area here, and we start seeing it, and our first 2 detections are actually going to show something on the rise. And the question for us, is this something which is interesting, or is it some boring, stupid star that's just going up and down? Okay? And so what we want to do is avoid the problem, say, for LSST, where we're paving over the sky, going through all this data, and we're finding something so incredibly faint because instead of being a 48-inch telescope, this is an 8-meter telescope. And the only thing we can follow up is a 30-meter telescope. We want to avoid that. Okay, so how many triggers can we handle and how can we optimize our follow-up is our big challenge. Okay, and so this for me is it. You have this fire hose of data and you're taking a hit off of it, and you want to do this in the optimized way. So Danny's going to talk about the machine learning and how we trigger on that. And I'll move this because I've seen people go into epileptic seizures watching this video. So I'll move it off of that back to this. But we have this data stream coming out. So not only do we want to tell if it's one of these 1 in a million events, but we want to characterize it beyond that. Is this a boring 1 in a million event, or is it an interesting 1 in a million event? And so then what we have to do is go back and trigger our pipeline to search at a deeper level. Say, run stacks, at a finer cadence, longer cadence. Say, is this something that's going up and down? Use data from other surveys in real time to tell us, oh, do we have imaging from something that's 1,000 times deeper, so we can see, is it a star? Is it a galaxy? What is this? Is it interesting to us? Those are the challenges that we face, and what that's going to do is create a feedback loop, and if you do the math on it, that feedback loop becomes as important, if not more important, than what we're doing in real time in terms of the amount of data that you're going through and the amount of processing. So our next stop in this is you're going to see the bulk of the machinery under this and how we find things with the machine learning. The next challenge for us is how do we take that to the next level and maybe apply machine learning to it to understand that feedback loop and what we want to go after. And there, I'll take any questions. Thanks. Yep.
The nice about this area, it's beautiful, it's poetry. What do you think about, what would this, how do you defend this to Congress, with the in the sense of what are we going to learn? I'm not saying this, I'm not being cynical.
No.
I'm just really curious about what we will learn from this beautiful discovery, right?
So, so here's my typical, so I work for the Department of Energy, subcontracted through UC. So why is DOE interested in this? Well, DOE is the largest funder of science in the United States. I do a modified version of weapons physics, okay? I study explosive transients. I do radiation hydrodynamic modeling of these type of transients. My graduate students have gone on to work in industry, they've gone on to work in academia, they've gone on to work at the weapons labs. This benefits them quite directly. They need these people, okay? DOE has always been interested in fundamental physics, understanding parameters from high energy physics, nuclear physics, etc. We do the same thing, just in a different way through astrophysics. So that's how we justify our DOE slice of the funding, is we're doing fundamental research, and then we provide benefits that go back into the weapons program, that go back into industry. The two students I have that are now working for Google, they're doing things that involve machine learning, real-time analysis, and feedback loops and pipelines that they worked on in grad school.
Actually, I'm sorry, I was more cynical sounding.
Oh, okay, yeah.
I just meant that I know that you have something deeper in mind about what you'll learn.
Oh.
You know what I mean? Like, yeah.
Personally?
Yeah.
So I am open to learning about anything that goes bump in the night. I want to understand the universe at a very fundamental level, and explosions are neat. I've always liked them when I was a little kid. I love blowing up stuff. So studying the biggest explosions in the universe has always been, you know, a great driver. There is nothing, and Josh will tell you this, when we were looking at that data coming off the telescope and looking at, there's nothing neater than seeing something that nobody else has seen before. And then when you do follow-up on it and you find a new phenomena which nobody has seen before, that's what drives me to understand the universe at that fundamental level. So that's my motivation.
So I wanted to know, what are the bottlenecks in the workflow that you have that are preventing you from seeing all that you want to see, or inferring all that you want to infer? Is it bottlenecks or missed events that you're worried? I mean, are there missed events because of that?
So it's mostly the next survey, ZTF, we will not be able to look at everything spectroscopically that we find. We did 3,000 over 7 years, roughly. So that's a few hundred a year, okay? We're going to find a few thousand a year. So what we want to do is use that expensive follow-up time to not miss out on anything that's interesting. So we have something that rises, gets brighter, starts falling. We want to trigger on that. That describes almost every astrophysical transient. How do we use that basic information with maybe other surveys telling us what's going on in the sky to say that's truly interesting or not, and do it in a statistical way so that we can say we didn't miss anything or we missed something. And then you also want to throw in sort of a randomized follow-up so that you understand any of your biases in whatever algorithm you wrote to say trigger or not trigger, because I can only do it on 10% of the objects that I can find, whereas here we did it about on 90% of the things that we found. How do we find those little golden nuggets out of everything? That's our big challenge now. We just we now own 65% of one of the follow-up telescopes. We're trying to decide right now what is the algorithm that goes in there to trigger something, what is the prioritization based upon the knowledge of the light curve and the various groups and their science goals. How do we meld? And that's a really challenging question, because one of the great things that we can do out of this is that when you're done doing the survey, you can go back and say, what are the rates of certain types of objects? These are really important. If you want to understand nucleosynthesis and where did the gold come from in the universe, well, you need to know the rates of the events that produce gold. And so therefore you need to have an unbiased sort of systematic survey which you can regenerate, populate it with those types of explosions, see how many you found, see how many there should have been, and calculate the rates. I'd like to do that and know I haven't screwed something up. So,
not to anthropomorphize too much, but I'm wondering about the sort of local and non-local effects of these things. I mean, if you're a carbon-based life form that depends on those carbon bonds sort of being intact for generations and generations, how close do you want to not be to one of these? And then again, there is this mixing over time where iron-like elements seem to have coalesced enough, been spread around enough to have it at the center of our planet.
So I have two interesting thoughts on that. The first is there are certain types of supernova that you really just don't want going off in your galaxy. And so the anthropic principle states that perhaps we're in a good spot because we're far out from the center, and that those types of supernova and most supernova blow up more towards the core of our galaxy, so there's something to be there. These supernova create sort of death rays that go across maybe half the galaxy. They're these, the ones that produce gamma ray bursts. You don't want to be in that cone of light that comes out there. But we've even calculated, and this was with one of the climate scientists before climate was something we no longer study at DOE, wanted to study the effect of a nearby supernova explosion on the Earth's atmosphere and how that would affect it. If you take one of the nearest stars that we know will go supernova, it's Betelgeuse in Orion, the one with the belt. And the bright red star on the shoulder, that's going to go supernova. It will actually be somewhere around half the brightness of the moon. That's about one of the closest stars that we know that will go supernova. That's not going to have a real effect on us. But if a star went off that was, say, the distance to Sirius, that would basically destroy life as we know it on this planet. So, you want to be in between.
A less catastrophic question. It seems like you're on the verge of a predicament where you're actually solving what used to be called the secretary problem, where you not only have to try to pick out the most interesting events, but you have to have in mind the fact that there may be a more interesting one coming, yes, and you should pass this one by, yep, and wait for the best one to come. Or it's like waiting for the best wave when you're surfing.
Exactly the problem. Literally, as I was walking over, I was doing a teleconference this morning, which was the following, and so I'll phrase it exactly in those terms. We have some very interesting, what we call TOO candidates. These will come in from other surveys, like LIGO, the Gravitational Wave survey, like the gamma ray burst. They're unlocalized. We'll have to move, slew the telescope, cover that portion of the sky, and then trigger follow-up on those events. And then we have the generic ones that we find, and we want to do a census of these to get our rates and do those well. So I proposed this morning that, well, the people from the TOO, and we only have so many hours on the night that we can do it, and it's not enough to do everything. So, a solution that I'm throwing out there now, but I'd love to hear from you guys as to better ones, because there was a large argument this morning. And I said, I'll come up with an algorithm this week, so maybe somebody can help me with this. I said, the TOOs have sort of a prediction for how many events they'll see, on order once a week. Okay, of course, statistics being what they are, sometimes you'll get 3, sometimes you'll get 4. What I'm worried about is the cuts that they've put in there are going to create 10 or 20 of these events. And now they'll start running into our census. So what I suggested was, well, they have some certain rate. Let's handle a 3 sigma bump over a week, but over the month they should get allocated the time that they should. And so we'll give them a priority that's in proportion to the time that they've used already, maybe weighted in a way over the month, okay? So yeah, they could be the highest priority during the week. If they haven't had anything, they'll go in immediately. If they're on their 4th trigger for the week, well, then they'll fall down into the, and so we're trying to weight that right now, and we're trying to weight the goals of doing the census survey over the whole sky down to a certain brightness level. And how do you optimize that? So that is a real question for us now, and we don't know the best way to solve it. But
There is a heuristic, if you're looking for the best event out of n events, that you should wait, you should let n over e pass by.
okay.
And then take the best one you see after that. This is, of course, is no guarantee that it gives you the best. It's just, it maximizes your probability.
Ability of getting, boy, that would be really disturbing if I said, yeah, we're going to skip the first n over e events. Sorry, Monsi, we're not going to trigger on your gravitational waves until we're really, yeah, okay, well, I could propose that. I think I'll get, yeah.
I mean, ultimately, it's the metric that I think everyone's trying to search for here as you're talking, right? The n over e probably makes sense if you only have, you know, one bullet in the gun to pull. But what happens is you have all these bullets throughout the night, so you've got a telescope night waiting to do follow-up, and if you don't use it, you've lost it. But then there's very expensive follow-up resources like at the Hubble Space Telescope level or the Keck Telescope level, where you do only have a few you know, chits that you can call in. And if you use that and you don't get good science out of it, eventually that winds up coming to haunt you. So there's the optimization metric over like the Rumsfeldian, you know, known unknowns and all the bread and butter. But then there's that other dimension which Peter is alluding to in these very large surveys, which is it's not Peter that's going to make the optimization metric over his science. The whole survey itself is beholden, because it has federal funding, to put out a whole number of transients which people within a given group may not be interested in, but another group may be very interested in, right? So there's a lot of garbage in our solar system, for instance, like asteroids, that nobody in, or very few people in the ZTF collaboration care about, but there's a whole cohort of people around the world that do. And there's certain types of asteroids that matter a whole lot and need very rapid follow-up. So there's this interesting problem now where there's so much data, and each person or each group has their own optimization metric, and how you allow each of them to basically, you know, glom that onto a survey is a pretty interesting problem.
Yeah, and the other challenge is some of them know the rates of their objects very well. These have been studied for a while. They know the uncertainties to 10%, okay? And others sort of have like a factor of 2. And that needs to be folded into this follow-up as well, is that they can't be dominating the time because their science is not as interesting as a whole as all the other science that we could do with these resources as well. So that's the other challenge that we have.
When you take a group of pictures in the sky, is there a way to use probability to say, okay, we only need to take 1/3 of the pictures and we should be able to hit that point? Like you got a 95% chance. So then you can get several different groups done and take.
So the answer is yes, if you are following up sort of the standard known type of explosions. I could do that. I could make people happy. That would work. If you want to find incredibly young things, then that goes out the door. I literally have to come back every few hours and hit that part of the sky because my window of opportunity is just a few hours. And so I'll miss it, you know. So yes, some of the survey can be optimized that way, but other parts of it, no, we just have to do the whole sky.
So actually a follow-up on that, if you look at, like, can you predict what portion of the sky something interesting might happen?
I can predict portions of the sky where some things won't be interesting for me, which is basically staring at our galaxy. No, unfortunately, these are totally chaotic, random events, and
Nothing else can guide like where start these
no,
supernovas.
no, yeah, that's unless it's what Danny will mention. There is one type of object that when we see one, we have a very good idea when the second one will come up. So we'll talk about that later.
All this optimization to track events that have a particular characteristic that you come to expect. Is there much room for discovering events of the kind that you haven't classified so far?
So this is the real challenge, that we want to make whatever our algorithm that goes in there, you almost want to randomly then 1 out of 50 events, just select something, throw it in, and do it, and just to understand, are we missing stuff that, yeah, we need to do something like that.
On your workflow diagram, I don't know if I noticed a true bit bucket, namely data that is thrown away, really thrown away, or not.
Nothing is thrown away. So that is one thing where we are different than a lot of other of the groups that have stuff, is that every pixel that we've ever taken is important, because we want to go back historically, say what happened there to find pre-outbursts. We want to go back historically to make a deeper image by stacking many images to see if this is a boring transient that's just going up and down and we just happen to catch it over here in a slightly brighter phase. So we just never throw away anything.
To follow up to that, I mean, so does that mean that you could make some discoveries in hindsight and not in real time?
We do that all the time, and that is a huge, huge area. Going back, looking at the data set, saying, we've done this right now, the first binary neutron star merger, we never knew what they looked like. We had theoretical predictions. I did not, even though it's my former grad student, I did not trust it well enough to say, let's optimize the survey to find these things, okay? Once they found it, oh, now we know what they look like. I can go back through the entire pipeline and say, anything else in there that was sort of down in the weeds that looked like this, I can dig a little deeper. We found one object that sort of looks like that. And so that is a very interesting number, because 1 plus or minus 1 doesn't tell you a huge amount of things about the rates, but 2 plus or minus root 2 tells you a little bit more. So. Okay. You are dismissed for cookies and tea.
Okay, we will resume at